Now, before we start talking about our machine learning tools, we wanted to spend some time about how we represent data in preparation for making use of these tools. Now, data can come from lots of different sources. It can come from sensors that are sitting out in the field somewhere. They can come from a database. They can come from data that's being entered by a user on a website. And it turns out there's a huge disconnect in the formatting of the data from this myriad of sources to the format that our machine learning tools usually rely on. So in particular, most of our machine learning tools want to make assumptions about the formatting of the data being very well defined. And in particular, our data should be cut into very distinct examples. Each example is a list of property values, and each of those examples has the same set of properties. For cases where we're dealing with supervised learning problems, we're also going to expect some sort of an expected label or expected value that our model should be outputting given the input example that is coming in. So on top of these issues, our machine learning tools also make some other assumptions. First off, they tend to assume that properties are numerical in nature. And they also assume statistical independence between the different examples. And furthermore, they want to be able to assume that the distribution that we're drawing our examples from is not changing over time. So a typical use case is that we're going to collect some data by sampling from the world for the last week. Then we want to build a model given that data. But then we want to be able to turn around and use this model moving forward into the future, which means that we're drawing samples at some other time period. And most of our machine learning models make an assumption that the new samples that we're drawing come from the same distribution as the original set of samples. And when this is not the case, this can be problematic. Okay, so that's what our machine learning tools tend to assume. The real world tends to violate a lot of these assumptions. First off, data can be very weakly formatted. We may be getting things in terms of CSV files, comma separated value files, or they may be coming in some other format. Properties are not necessarily numerical. We could have enumerated types. So for example, we might have a feature that represents the shape of something that we're detecting. And so possible values are things like circles and squares or rectangles. And we need to have some sort of a way of making a transformation from these enumerated values to the numerical world so that many of our machine learning tools can make use of them. It's also the case that values are not correct. So a sensor might start to fail and begin to lie, say, about the temperature or the humidity at a certain point in our mesonet grid. Values can also be missing. So if I have a battery of sensors, I might lose power to that computing system for some amount of time. And in those scenarios, we have no values. Those might actually be recorded explicitly as incorrect values. There are also some scenarios where different examples can have different sets of properties. And so this violates our assumption about the uniformity of our different examples. And most machine learning algorithms will have trouble with this, and so we'll have to address this in our pre-processing. There are some algorithms out there, though, that can actually deal robustly to these types of situations. And then finally, the real world, the statistical distributions that we're drawing examples from do tend to change over time. Customer buying habits change over time. Things change in the climate. And so we want to at least be aware of these types of situations and be careful about how we apply our models when we are facing a situation where these distributions do change. So the fact that we have this big gap between the raw data and the data formatting that we need for our tools implies that we have to take some steps in doing this transformation between the two. And as it turns out in practice, we can actually end up spending a tremendous amount of our project time on this particular step. And how well we do this can actually affect how well our machine learning algorithms will perform in the future. So it's actually worth spending time getting this right. Also, as part of this step, we actually have a real opportunity to really understand the nature of the data that we're facing. One of the things that often happens in the machine learning world or the data science world is that people will tend to blindly pick up data and throw machine learning algorithms at it without really understanding what the data mean or what the predictions mean that they're trying to make. And this particular step is a real opportunity for us as practitioners to spend time understanding the nature of the data, making sure it's actually correct. And this gives us a better opportunity to make sure we get the transformation right. And it also means that we probably will make some better choices when we are when we are selecting our machine learning tools. Okay, so this is where we're going over the next set of videos. I want to talk about several different Python packages that provide different steps in this process. This conversation is definitely not comprehensive. It's intended to give you a very quick look at the different packages and some of what they can do. I really encourage you to spend time with the documentation. The documentation for all three of these packages is actually quite good. The Pandas package, it's all about bringing data in from a variety of different formats and then allowing us to do a certain degree of massaging of that data. The numpy package is all about the efficient representation of our numerical data. This turns out to be the basis for a lot of our machine learning algorithms. And the matplotlib package, it provides a whole set of visualization tools that look and feel a lot like the MATLAB tools that many of us are used to. So let's drill down into the Pandas toolkit a little bit. It does file input and output. We've already talked about CSV files, these comma-separated files. Those of you who've done work with things like spreadsheets, one of the formats that spreadsheet programs can take in or generate is CSV files. This is actually the original file format that's used by things like Excel. Pandas also provides a set of hooks for visualization. What's actually underlying those tools is matplotlib itself, but Pandas gives you a quick way to access those. Pandas will also compute basic statistics for you so that you can understand what your different features are doing, temperature or wind speed. It also allows us a certain amount of capabilities that feel a lot like database kinds of operations. So we can do things like selection of data and repairing of data that might be problematic. And in fact, there are a variety of operations that feel a lot like the SQL kinds of operations that some of you are used to using. The two classes that we'll really focus on from Pandas are the series and data frame class. The series class is all about representing 1D data. So this is a representation of an array. We can have values that are indexed either by some numerical value, so 0, 1, 2, as we're already used to in representing arrays, or if you've set things up properly, you can also address the individual values using strings that are associated with each of the indices. The data frame, we'll be spending most of our time with this. This is all about representing two-dimensional data. It's very typical for us to be representing data in this format where our rows are different examples and our features are different columns. And just as with the series data, we can either index the dimensions numerically, or we can use, say, a string to represent an index. So for example, if our CSV file has a header associated with it where the columns are named, we can automatically address a particular feature by referencing that name instead of the particular column number that we're looking for. Data frame gives us the ability to do a bit of exploration once we've brought data in. So we can look at what the index names are for our rows and columns. And then we can also compute statistics. Most useful are down our columns, but one could also compute statistics along our rows if we wanted to do that. We can also sub-select data. We might decide at some point that we only want a certain number of columns, a subset of columns from an existing data frame, and we can create a new one very easily by selecting the columns that we want. We can also address the problems where we have data that are invalid. So we can detect those and either make choices to remove or repair the individual values. We can repair the individual values, or we can actually remove the offending rows, or sometimes we might just remove the columns. And then one of the final steps that we often take is that we then transform our data frame data into a numpy array, and then this is then the format that we're going to be using with our machine learning methods. NumPy is all about, first off, representing tensors. So vectors are arrays. They are one-dimensional tensors. Matrices are two-dimensional tensors, but we can actually represent three-dimensional, four-dimensional tensors as necessary. NumPy also provides a whole set of different operators that we can apply to these tensors. So we can do things like compute matrix inverses. We can do singular value decomposition on a matrix. And it turns out that these operators are really the basis for the implementation of our machine learning tools within scikit-learn. So it's actually worth spending a little bit of time perusing through the documentation for NumPy as well, so that you understand what its capabilities are. Okay, so that's a top-level view of a few different packages. We're going to do some very explicit examples, but first I want to spend a little bit of time talking about a data set from my own research that we'll be using within these examples.